Good morning, all of you. Suryawanshi ma'am, shall we start?
Yes, ma'am, we can start.
Okay. Okay. So, good morning to one and all. Respected Principal Sir Dr. D.B. Ufade Sir, our HOD Khedkar Sir, all staff of members of IT department, and my dear students. On behalf of MVP's RSM Polytechnic and Department of IT, I am Ms. Reena More. Welcome you all for today's guest lecture of Digital Techniques and Microprocessor organized by our IT department. So today in our session, we'll see the topic of the assembly language programming using 8086. So assembly language, it's a low-level programming language for a computer or other programmable device specific to a particular computer architecture. And to enlighten more on this topic, today we have an expert, Professor Sujata Suryawanshi ma'am. Ma'am is working as assistant professor at NDMVP's KBT College of Engineering from last 10 years. She has completed her BE in IT from Pravara Rural Engineering College, Loni in 2008 and completed her ME in computer from Kekewa College of Engineering in 2014. And I'm sure that you all will enjoy this session and will get very much insight of this topic. So on behalf of RSM Polytechnic and IT department, I welcome Professor Sujata Suryawanshi ma'am and request her to start the session.
Thank you. Thank you so much, ma'am. Thank you for inviting me as a guest lecture. So, good morning, one and all. Am I audible to all of you?
Yes, ma'am.
Okay. So, thank you. We'll start our today's lecture. As Reena More madam said, she has given the introduction. That is myself, Sujata Suryawanshi from MMBP Engineering College, Nashik. Just let me share my screen first. We will start in a moment. Yes, is my screen visible to all of you?
Yes, ma'am.
Okay, thank you. So, I'm working as an assistant professor in NMVP Engineering College, Nashik. So, in the today's session, these are the points I will cover. That is, first one is introduction to the programming model of 8086. And second one point is addressing modes of 8086. Third one is group of instruction set. And the last one is assembly language program. We will see one program, simple program written in assembly language, and we'll see the meaning and how to write assembly program. So we'll cover all these contents. Start with the first one, that is programming model of 8086. Directly jump on the programming model of 8086. First of all, we should know what do you mean by computer. In the current situation, we all are aware with computer. We all are using computer in day-to-day life. Okay, but we should know the internal part of the computer and the functional part of the computer. Okay, we know the use of computer. What is the use of computer with the help in the IT or computer engineer perspective. Whenever we are using computer, we need to design or execute the task. Okay, so here first of all, what do you mean by computer architecture and computer organization? Okay, so first one is the computer architecture. It describes what the computer does, and organization describes how it does it. Means in the organization, the procedure is given, and in the architecture, how the particular components are components are available in the architecture and assembled in the computer. So first one is computer organization. It describes the function and the way computer components are operated, and the way they are connected together to form the computer system. Here, the different components are present in the computer system, and how that components are connected together to operate or to execute specific tasks. This is given by the computer organization. So then next one is the computer architecture, the structure, the internal structure and the behavior of computer as seen by the user. User means we are using the computer. That's why we are considered as user. Then in the user perspective, what is the structure and behavior of the computer? It is given by the computer architecture. Then it describes or it includes the instruction formats, the instruction set, and the techniques of the addressing mode. So, as we all know, the if you want to design the program to find addition of two numbers, then we need to use any higher level language or any programming language. Either you can use C programming or Java programming or C++ programming. Okay, so each programming has a specific syntax. Okay, so within the given syntax, you need to write the program, and then we have to give the program as an input to the system to get the output from the system for the execution purpose. So here in the assembly language is used, it is a hardware language, is low level language is used in this COA architecture. Okay, so for that purpose, again different formats are used or given, that is the instruction formats and the instruction set. Different sets are given, means we can use the syntax, the proper syntax to write assembly program. So these are included in the computer architecture. Then we'll directly go on the programming model for the microprocessor. It shows various internal registers that are accessible to the programmer. Means if programmer want to do program in assembly language, then that programmer has to access or use different registers, internal registers present in the microprocessor while you are writing the programming in the assembly language. So the programming model for the microprocessor, any microprocessor, it shows the various internal registers that are accessible by the programmer. Now, in general, each register has this special function. Means if the microprocessor, suppose we are considering 8086 architecture, then it has different registers. Then if we consider different architecture, then that particular architecture or the microprocessor has different registers. Okay, but each register has the special function, specific function. So this is the functional unit of any computer. In the computer, there are different units present over here. Okay, so these two units are present in the IO units. Here in the IO units, input unit and the output units are there. Means whenever we are using computer, we should give some input to the computer and to execute the task, and after execution by the computer gives you output, and to show the output or to give output, output units are required. Okay, I hope you all are aware with input and output unit of the computer. Then next means input units are, you can give input through keyboard, you can give input through mouse, or you can give input through scanner. Okay, then output units are very popular and very important. Output unit is the monitor from which we can get output. Then printer is also one of the example of output unit. Then next unit is the memory unit. Means whenever we give input to the system, to first of all we'll see one example. Suppose we want to find out addition of two numbers, then we write the program in C programming language. Okay, and we give the input to the system, then that particular program is written in high level language, but system don't understood the language. So that particular program should be converted into the low level language, and after that, that program is stored in memory unit. Okay, memory unit is composed of different memory locations. Okay, so as per specific, in the specific memory location, the program is going to store, and after that, one by one program. After that, that program is divided into different micro operations, and that one by one micro operation is faced by ALU unit, which is available in the CPU or the processor, central processing unit. This central processing unit is composed with two different units, that is ALU unit and the control unit. Here, all the operations, ALU operations are performed by ALU unit, and to perform the specific task, ALU requires different variables or the data. So that particular data or different variables can be accessed from memory unit through control signals which are generated by control unit. Okay. So the control unit generate different control signals, and through that control signals, data is accessed by the ALU unit. So this is the functional unit of the basic computer. Now we'll see the programming model of 8086 architecture. So it is collection of different registers. There are, this is the programming model of 8086, where these first four registers are called as general purpose register. Means it is collection of general purpose register and special purpose register. Okay, so first four registers are called as are in the category of general purpose register. First is the AX or EX. The size of this EX is total EAX is of 32-bit register, and this is called as 16-bit register, start with 0 to 15. Okay, and again we can access complete EAX, or we can access, or the programmer can access lower bit of AX or higher bit of AX. AL stands for accumulated lower bit, and AH stands for accumulated higher bit. Okay, so EAX is complete 32-bit data or the register. We can store 32-bit in AX, and we can store if our data or the operand is of only 8-bit, then we can use only AL, that is lower bit of AL. If your input data is of 15 or 16-bit, then you can consider this AH. Okay, that is higher bit, means including AL and AH. So this is the complete programming model of 8086 architecture. We will see each and every register one by one. First one is the, here total 4 general purpose registers are there. Then 4 segment registers are there. 2 pointer registers, 2 index registers, 1 instruction pointer register, and 1 flag registers. Means with the help of the combination of these registers is present in the programming model of 8086. Okay, so we'll see first one, that is the data register. The data register, there are total 4 data registers: AX, BX, CX, and DX. Here in this diagram, the registers are given in the 32-bit size, but while I'm explaining it, I'm considering only 15-bit. So AX is of complete 16-bit register. Again, BX, CX, and DX. All the data registers are in the 16-bit registers, which is called as general purpose register, which is used to store the operands and results in the ALU operations. Okay, so if you want to add it to numbers, so the instruction written in C programming is C is equal to A plus B, where C is the destination variable and A and B are the input variable where we can give input. So if A value is 5 and B value is 6, then output 11 will be stored in the C variable. So for that purpose, to store the operand A and operand B and to store the result, these registers are used. Means the data registers A, B, C, and DX. These registers are used to store the operands, results, and the intermediate results. If you want to use the results for the further operation, then we can store that particular result in the intermediate result also. Okay, so each can be accessed as whole as a AX, or we can simply access as a lower bit or lower or upper byte, either AL or AH. Okay, so this is AL and AH. AL is of bit 0 to 7 and AH is from 8 to 15. If your value or the variable is of only 8 bits, then start with 0 to 7, means you can simply use AL for the operation. Okay, so we'll see first one is the accumulator, that is AX resistor. It is also called as accumulator resistor. It is used in arithmetic and logic operations, and also it is used for data transfer instruction. Means if you want to transfer data from one register to the another register, then we can also use AX, that is accumulator resistor. In the manipulation and division, one of the numbers involved must be in AX or AL. Here means if you want to add two numbers and store the result in another variable, then we should, means if C is equal to A plus B, this is our operation, then A and B, these are the two internal variables, but one of the internal input variables should be stored in accumulator. Okay, it is compulsory to store one of the input variable in the accumulator. Either you can use AX or AL as per the bit size of that particular variable. Okay, so this is the example. We will see the syntax or instruction or opcode for assembly language, but this is, we'll see one example here. Add is the opcode or the instruction we can consider for addition. So this is the instruction, add space AX comma AX. So the meaning of this instruction is what? It will find addition of these two addresses or the operands are given. So AX is equal to AX plus AX, means whatever the addition or the result we get, that result will be stored by first operand only, not the second operand, because the first operand is treated as input and the output also, means AX is equal to AX comma AX. Okay, so second one resistor is BX resistor. It is also called as base resistor. So if we want to add two numbers, but we don't know the specific value, we want to give the address or the location where that variable is stored. So in this case, we can use base resistor. Okay, here it is used to store the value of the offset, and this resistor is used in base index or the resistor indirect addressing mode. Okay, so here we'll see the example. Suppose move BL comma 500H. Here 500 is not the value. At the location 500H, the variable is stored or the value is stored, then that particular value will be moved to variable BL or the resistor BL. Okay, so this contains the resistor. Okay, means this 500 value is moved to BL, but that BL is not the value, it shows the address of that particular variable. Now the next resistor is CX resistor. The basic purpose of CX resistor is in the looping. Okay, so if in the C programming we are using we use for loop or if loop or any type of control structure we are using. Okay, if you want to execute the specific statement multiple times repetitively, then you can use this counter. So in the assembly language, counter means loop. Whenever we use loop, then we should consider the index which can be incremented from 0 to 5, suppose, then this CX resistor is used. If CX is equal to 5, then that particular loop will be executed 5 times. Okay, in this way we can use this CX, that is counter resistor. We'll see one example here. Suppose move CX comma 5, means right now CX value means this counter register has value 5, means whatever the statement written in this loop, that particular statement will be executed 5 times and Cx will be decremented till 0. Okay. So next register is Dx register. It is also called as data register. It is also of 16-bit register. Then it is used in multiplication and input or output port addressing. Suppose you want to do multiplication, then for that multiplication, here mul operation you can use, or the instruction you can use mul space dx, where dx, that is data register, is used to store the result. If the result generates the carry, and that particular carry means, suppose here bx is used, okay, and bx is having size 16 bit, and if your multiplication generates more than 15, means the range beyond the range of the bx, then the remaining or the upper portion will be stored by dx register, that is data register. Okay. So for that purpose, data register is used. If the range is not sufficient to store the result of multiplication, then the upper byte will be stored by data register. Then next one is the segment register. There are total 4 segment register, that is the CS, DS, SS and ES. CS stands for code segment, DS stands for data segment, SS stands for stack segment and ES stands for extra segment. All the segments are of size 0 to 15, means total bits are 16 bits. Okay. So the code, data, stack and the extra segment. The segment register points to the starting address of the memory segment. The maximum capacity of the segment may be up to 64 kilobyte. Size, total maximum size is 64 kilobyte, and these are the registers where you can store the code, you can store the data. If you want to store the data in stack, then we should use stack segment register and the extra segment register. Okay. So we'll see all the segment registers one by one. First one is the code segment register. It is used for addressing memory location in the code segment of the memory. Means suppose system has to store code written in the assembly language or code written in the machine language, then that particular code will be stored by code segment, and where the executable code is stored, and one by one all the codes are accessed by the ALU to execute. The second one register, segment register, is called as stack segment register. Then if instead of using register, if or any instruction, if you want to use stack for the operation, then all the data is stored or the variables are stored in the stack segment register. The stack segment is that segment of memory which is used to store the stack data. Now, the next one is the data segment register. It points to the data segment of the memory where the data is stored. Means the data code is stored by code segment, and the data required to execute that particular task, that data is stored in the data segment register. The next one segment is the extra segment register. It refers to the segment in the memory which is another data segment in the memory. Means if the data segment is not sufficient to store the data, then extra segment register is used. Then the next one is the pointer register. First pointer register is the stack pointer register. Whatever the data stored in the stack segment register, which can be pointed, this stack segment register, which can be pointed by the stack pointer register. Okay, this is stack pointer register pointing to the programmer stack, and the programming stack points to the topmost item. As we all know, the topmost element is pointing by the top variable in the stack. Okay, so next one is the BP register, that is base pointer register. This is also 16-bit register. It is primarily used in accessing parameters based on the stack. So what the parameters are required for the execution, and where it's stored, that base pointer, in the base pointer, that particular parameters can be passed by the stack here. Okay, so it is pointed by the base pointer. Then next one is the index register. There are again different index register. First one is the source index register. So this is also of the 16-bit register. It is used in pointer addressing of data and as a source in some string related operation. Its offset is relative to the data segment. Means whatever the data stored in the data segment, if we want to consider or we want to use the data stored in the data segment, then that particular data will be pointed by the source index. Okay, source index register. Then the next one register is the DI register. It is similar as SI register. It points to the destination index only. Okay. So the next one is instruction pointer. The instruction pointer register, it points to the instruction which is to be executed. Okay. It stores the address of the instruction which is to be executed by the ALU unit. Its content is automatically incremented when the execution of program proceeds further. Means suppose 4. Suppose 004 is the location where the current instruction is stored, then that particular instruction is executed currently by the ALU unit. And once that particular the current instruction is stored, then that particular instruction is executed currently by the ALU unit. And once that particular instruction is executed and the result is generated by ALU, then that particular pointer will be incremented by 1, and then the next instruction will be executed and stored by the instruction pointer. Okay. So the content of IP and code segment register are used to compute the memory address of the instruction code to be fetched. Means from which location the instruction is fetched for the execution, it is depending upon the content of IP, that is instruction pointer, and the code segment register. Once the content is present in the instruction pointer, means that particular instruction is to be executed. Okay, it is not executed right now or currently, and then the data is and the code segment register is stores the code, that the instruction. Okay, so these two pointers are used to find out the memory address of the instruction to be fetched to the next instruction. Okay, so this is done by the fetch cycle. There are different cycles for the operations. First one, fetch cycle is used, that is to fetch the current instruction for the execution, and after fetching the instruction, execution cycle is there. After fetching the instruction, whatever the operators required or the variables required to execute that, that's why the memory cycle is required for communication from ALU unit to the memory unit or the cache. Okay, where the data is stored. That particular data will be accessed by ALU unit for the operation to execute that instruction, and then the data should be stored or the result should be stored in the memory. So these are the cycles, but here this particular memory address of the instruction is computed in the fetch cycle only. Now next one is the flag registers. There are total flag register is the special purpose register depending upon the value of result after any arithmetic and logical operations. The flag bits become set 1 or reset 0. Means as per the value of flag, it is changing. Okay, so here total, this is the format of flag registers. Here total 16 flags are there, but not all are used in the 8086 architecture. We'll see one by one all the flags. O means 0 flag. There are total 9 flags in 8086, and these are divided into 2 different types. So first one is the status flags, the flags which shows the status of the result, that is called as status flag. Okay, so we'll see there are total 6 flags out of 9 are used as a status flag in the 8086. Okay, so we'll see first one is the sign flag. S stands for sign flag. If the MSB is 1, then number is, we know how to represent any number in sign in the form of sign number. Okay, if the MSB bit of 8-bit number is 1, then that particular number is negative, and if MSB bit is 0, then that number is positive. And when you find out the addition of two sign numbers, and if the result is having MSB bit 1, then the result is negative. Okay, so in this case, sign flag will set to 1, and if your result is positive, then the sign flag will set to 0, and that is the reset. Okay, then second one flag is the 0 flag. Z stands for 0. It is again 1 for 0 result and 0 for non-zero result. Means if we are finding subtraction, we are writing one instruction for subtraction, and if the result is 0, then your 0 flag will set to 1, and if your result is non-zero, then it will set to 0. Then next one is the auxiliary carry flag. AC stands for auxiliary carry flag. Then 1 means 1 when the carry out from 3-bit on addition or borrow into bit 3 on subtraction, and 0 otherwise. Means auxiliary flag is equal to 1 when you add two 8-bit numbers. Okay, and if carry is generated in after 3rd bit, okay, and if borrow is generated in the 3rd bit in the subtraction, then auxiliary carry flag become 1, otherwise it become 0. As per the carry is generated in the 4-bit nibble. Okay, means 4-bit collection of binary number is called as, group of 4-bit is called as nibble, group of 8-bit is called as byte, and group of 16-bit is called as word. Okay, so if the carry is generated in one of the nibble, then that particular auxiliary carry bit will be 1, and if it generates carry is not generated, then auxiliary carry flag will be 0. The next one is the parity flag. Okay, so 1 for the accumulator has even number of 1 bits. Means once you get the result, and if the result is having even number of 1 bit, then that particular parity flag will be 0. And if the accumulator has odd number of 1, then parity flag will be 0. Means parity flag is equal to 1 if the result is extended, means total. If you are considering sign bit, so 0 means the positive number. Again 32 can be represented by this. Okay, so this 32 is also having sign bit 0, so 32 is also positive number. But when you add these two, AL comma BL, okay, when you add these two values or values stored in these two registers, you will get the answer 82, and 82 can be shown in the binary form, that is 1 0 0 0 0 1 0, but the total all 8 bits are reserved to store magnitude, so sign bit is not there. And if we are considering sign arithmetic, then the sign bit is reserved only, means MSB bit is reserved only for sign bit. Here 1 is due. Okay, but right now it is level into so I am pressure in the is the B after the operand. Here A and B, these are the operand, and operation is plus. So first write down first operand, then second operand, and then operator. So you can write down the expression in the postfix from, this is AB plus CD plus into. Okay, so when you find out the postfix expression of the given infix expression, then we need to write down the expression in the assembly language. First one is push operation. If just scan this expression written in the postfix form, you have to call pop operation 2 times, means pop 2 variables stored in the stack and perform the operation. And after performing the operation, you need to again push the result of the operation into the stack. Here initially A, you have to push A, means top is pointing to A right now. Then next is also variable B. So again push B, means right now top is pointing to B because top is incremented by 1 every time when you pushing the data into the stack. After that, next token is what? Next token is plus, means the operator, not the operand. So you have to perform the operation or the task. Then addition is there. So use this add method, add, and then simply add will be performed on the variables A and variable B. To get that variables, we need to use pop operation, pop B, then pop A, and then find out the addition and store the result in the top. Okay, means in the stack. Again for C and D, and again find out the addition because next token is plus. And after getting this, next token is multiplication. Right now, your stack is having addition of A and B and addition of C and D. So again, call pop operation 2 times and then find out the multiplication. And that multiplication is pointing to top now, and that top will be moved to mx. That is, x is the variable, which is mx is the memory location of the x, any memory location of the x, because the result is stored in the x in the given expression. That's why mx is equal to top. In this way, you can write the program or the instructions in zero address format. Okay. After that, next one is the one address instruction, where only one address is given. Okay, means only one address is given here. We can see opcode. Opcode means the instruction. Then operand address means only one operation operand is there, and mode we can give mode. In which mode we can write the instruction. Either you can write read mode or the write mode. Okay. So we'll see the same example, that is x is equal to a plus b into c plus d using the one address instruction. Then how will you write one address instruction for the same example? Here, one address we can consider in the instruction. Okay. So first of all, accumulator we need to use, because first here only one address we need to use. Okay, but the operation needs two operand. Okay, so c is equal to a plus b, means addition of a and b. Two variables are there, but one of the variable is stored in accumulator, so no need to specify that accumulator in the instruction. Only you need to specify the second one variable, okay, which is not available in the accumulator. So this CPU already knows that one operand is in accumulator, means first of all a variable is there. We need to store that a variable in accumulator. So load a. This is the instruction. Load a means that a variable will be loaded in accumulator. Okay, AC is the register, accumulator register. So whatever the value stored in variable A, that value will be stored, loaded in the accumulator. After that, add B, means here I am using only instruction add and the second one variable B, because A is already available in the accumulator. No need to specify that variable A in the second one instruction, because we are writing or we are considering only one instruction, one address instruction. Okay, so only one variable should be there while you are writing instruction. So add B means here A is available. No need to specify that A, because that A is available in the accumulator. Means the result of this add B is equal to AC is equal to AC plus MB, where B is the variable memory location where the B is stored. Okay, then that particular variable will be added with accumulator, and the result is also stored in the accumulator itself. Means here AC, the accumulator is considered as source and the destination. Okay, means after adding, the result will be stored in the accumulator itself. After that, next one is T, because we want to use accumulator for the further operation, means for the addition of C and D. So for that purpose, consider one variable that is temporary variable. So store T means whatever the value stored in accumulator, which will be stored in temporary variable T with the help of instruction store T. After that, after storing that, again consider the first, second and third instruction. Similarly, for the addition of C and D, because load, we have to load C into accumulator, then add D means addition of C plus D, because C is available in the accumulator, no need to specify it. And after that, multiply T means accumulator is having right now addition of C and D. Okay, so no need to store the result of addition of C plus D, because we want to use this for multiplication also. So accumulator is having addition of C and D, and after that AC is equal to AC into MT means T is having value addition of A plus D, and accumulator is having value C plus D. So only use mul instruction, that is multiplication and T, because accumulator is having value C plus D. Okay, so with the help of this instruction, AC is equal to AC into M of T. Multiplication of these two terms are done with the help of this mul instruction. And after that, store means we want to store the result in X variable, that is the destination of variable. So use store instruction where the result will be stored, and result is available in the accumulator. So accumulator will be stored in the MX, that is memory location of X. Means these are the different instructions required in one address instruction. Okay, so only one instruction should be there while you are writing instruction in the one address instruction. Then the second one is variable is available in the accumulator only. Next one is to address instruction. In the to address instruction, no need to store the result in accumulator. Simply use to address. First one is destination address and the second one is source address. Okay. So here again, we can consider the same example, that is X is equal to A plus B into C plus D. Then simply no need to use load instruction here or store instruction here. Simply move A R1 comma A. So R1 register is used to store value of A. Then add R1 comma B. R1 is having right now value of A, and then B is the second one variable. After that, addition is we are getting addition of A and B, and result will be stored in the first address or the first operand, which is R1. Okay. After that, again C is moved to R2, and then R2 comma D will be added. Means C plus D. C is available in R2, so R2 is equal to R2 plus R1. Means result of addition is stored in R2 variable. Again, after that, multiplication is there. So mul R1 comma R2, where R1 and R2 is having value of addition of A plus B and C plus D, that is R2. So multiplication is there, and after getting the multiplication, that result will be stored in the first variable, that is R1. Okay, and after that, that R1 will be moved to X1, because our result will be stored in the X variable as per the expression given. Okay, so these are the instruction required, or we can write these expressions in to address instruction for the given expression. Okay, so after that, third address instruction is there. Three address instruction is there. Means while you are writing instruction, we can consider three addresses. Okay, instead of two or one address, we can consider three address. Means only write down opcode, means the instruction name, and after that we can consider three addresses. First one is the destination address, and remaining two are the source address, which will be used to give the input of the given instruction. Here the same instruction is there, and these are the instructions written in three address instruction. No need to move the data in register, any one of the register. Simply consider R1 comma A comma B to perform the addition of A plus B. Means after adding A plus B, result will be stored in R1. Similarly, for the third one, addition will be performed A plus B and result will be stored in R2. And the last one is the multiplication. Again, R1 and R2 are having addition of AB and CD respectively. And after that, that addition will be moved to X, that is the result variable. Here, what you can say, with the help of three address instruction, number of instructions requirement is very less. Okay, means only three instructions you have to write for the same expression as compared to the previous, that is one address, two address instructions. Okay, but the cycle for the execution our requirement is same, means every time B is available in the memory location, that should be available, that should be moved to the accumulator. Internally, the time requirement to execute all these tasks are same as the previous registers. Only the memory, sorry, the byte requirement or the bits required to show the address is less in the three address instruction as compared to two address instruction and the one address instruction, because only three instructions are required to write for the given expression as compared to the previous one. The previous address instructions will require more than three instructions. Okay, but time requirement is the same for all the address instruction, means one, two, or three address instruction. After that, once you write the instruction, you should know what is the addressing, how to address the how to write or how to give the operand for the instructions. Okay, so with the help of addressing mode we can give it. Why to study addressing mode? The addressing mode helps us to understand the types of operands and the way they are accessed while executing an instruction. Means when we are writing any instruction, then what type of operands you are considering or you are giving to the while you are writing the instruction, it is depending upon the addressing mode. What type of addressing mode you are using, with the help of that you can write the instruction. Okay, so there are total 8 different addressing mode. First one is immediate addressing mode, direct addressing mode. We will see all the addressing mode one by one. First is the immediate addressing mode. The name suggests immediate, means the data stored in the specific address. Okay, so the immediate data means suppose 100 is the location and 22 is the value stored at the location 100. Okay, so 22 is the immediate value which is stored at the location 100. So if the immediate variable or immediate value is used, is the part of your instruction, then that particular mode is known as immediate addressing mode. So we will see one example here. Suppose instruction is move AX comma 10 ABH. Means what? This AX is having value 10 ABH. Means this value is available in the hex form. Okay, this is number, hex number is given. Means the data is available in AX register is a hex number, and if that particular value we want to move in the AX, then that particular addressing mode is known as immediate addressing mode. Means we want to move this 10 AM into accumulator, and after executing this, your accumulator will look like this. Means accumulator is having value 10 ABH. Okay, so if the immediate value or the exact value is a part of your instruction, then that particular addressing mode is known as immediate addressing mode. Understood? If you want to move, suppose 50, okay, 5050 into the accumulator, then how to write the instruction? Move space AX comma 5050. Means I want to store 5050 into accumulator, then you need to use simple the instruction. Simply 5050 is the part of the instruction. That's why it is known as immediate addressing. Next one is direct addressing mode. Means what? Here move AX comma 5000H, where this 5000H is given in the bracket. Okay, the bracket indicates it is not the value. You should consider it as a reference. It should consider it as a address of the memory. Okay, where the data is stored. Means if you write move AX comma in bracket 5000H, then your AX should have value 22, because 22 is available at the location 5000, and my instruction is having 5000 which is written in the bracket. Means in the bracket is there, then that particular value is not the immediate value, it is the reference value. Means the address is given in the instruction. That's why it is called as direct addressing mode. Means the direct address is given in the instruction, then that is known as direct addressing mode. Okay. Sorry. After that, the next one is register addressing mode. Here, simply registers are used. Means BL, move AL comma BL. The destination register is AL, and we want to move whatever the data available in the BL, which is moved to AL with the help of the first one instruction. Okay. And if you want to access complete 16-bit data, then we need to use AX. Understood? Here, with the when you execute first instruction, that is move AL comma BL, simply lower byte of BL will be moved to AL. Means only AB will be moved to, means instead of 33, AB will be stored here. Okay. And 10 will be remain same, because we are considering only AL, means only the lower byte. And if you are writing AX, that is move AX comma BX, then the complete 16-bit register will be moved to AX. Means total AX will look like AX is having value 10 AB after executing the instruction move AX comma BX. After that, register indirect addressing mode. Indirect means direct value is not given, but whatever the value stored in the BX, that value is the reference where the data is stored. Means move AX comma BX. So here BX variable register is there. At that register 5000, this value is stored, but do not copy or move this 5000 as it is into AX. Simply consider this 5000 as a reference. At that particular address, the specific value is stored, and we want that value only, not 5000. Okay. So here 5 at the location of 5000, 22 variable or 22 value is stored. That value will be moved to AX. So after execution of this instruction, AX will have 22, not 5000. Understood? Okay. After that, next one type is, just tell me one example is there, move in bracket 7000H comma CX. So tell me what is the addressing mode of the given instruction. Can anyone tell me? Yes. What is the addressing mode for the given instruction? Move in bracket. Bracket is given 700H comma CX. Means whatever the value stored in CX, that will be moved to the location where 7000 memory location is there. Okay. So here direct addressing mode is there. Means whatever the value CX is having 4056, that value will be moved to 7000 location. Means this 22 will be replaced by 4356. Okay. So it is called as direct addressing mode. After that, the indexed addressing mode means in if the index registers are the part of the address or the instruction, then that particular mode is known as indexed addressing mode. Means here move AX comma SR, but here bracket is given. So don't consider the immediate value of SI and simply move it into AX. Instead of that, you need to consider the value stored in SI as a reference, and at that reference, what value is stored, it should be moved into AX. Okay, that's why it is called as index addressing mode, because the index register is the part of the instruction. Okay, after that, registers relative addressing mode, where 550x in bracket bx. Okay, only change is there. So in this instruction, offset is given, means we don't want the data stored in the location 5000, we want the data stored in the location 5000 plus 50, because 50 is given in the instruction. So 5000 is available, 5000 is present here for the bx variable. So 5000 plus 50 is equal to 5050. So we want the data stored in the register, in the memory location 5050, that is 5050. 44 is there. So we want that data to move at the accumulator, that is 55. Means here, with the help of this relative addressing mode, we need to find out final index address with the help of offset given in the instruction. After that, the base plus index addressing mode is there. The next type is base plus index. Means the base register and the index pointer is the part of your instruction. Then that addressing mode is called as base pointer instruction, where bx means bracket is there. That's why you need to consider address instead of value. Okay, and consider plus operator, means addition. Bx plus si. Bx is having 1000 and si is having 2000. So 1000 plus 2000 will get the final index where the actual data is stored, means 3000. At the 3000 location, 12 is given or 12 is stored. Then we want to move this 12 in the accumulator. In that case, base plus index addressing mode is used. After that, base relative plus index addressing mode, where relative means offset is given. Okay, so you need to just add offset plus the address of bx and address of si. So bx is having address value 1000, si is having value 2000, and we need to add offset, that is 50h, to get the final index address, that is 3050, and the data stored at the location, memory location 3050, which is 12. We need to move this 12 into the accumulator. Means after executing this instruction, accumulator is having value 12, which is stored at the lower byte of x only. After that, the next one is machine instruction. So here, how to write the machine instruction, we will see directly. Every program directly executed by CPU is made up of series of some instructions. So how to write the instruction? We have already seen some examples of the machine instruction, but we'll see the syntax or general format of the instruction, machine instruction. That is, first one is the label. Mnemonic. Mnemonic is also called as operation or the instruction or the opcode. And then the in bracket, we can give operand, two operands. First one is the destination operand and second one is the source operand. And after that, semicolon comments. If you want to give comment for that instruction, then you need to first initialize with semicolon. Means it should be start with semicolon only. And this is the label. Whatever the word given in the bracket, these are the optional. These are optional, means it is not compulsory while you are writing the instruction. Compulsory is what? Mnemonic or the opcode is compulsory. You have to write down that opcode only. Okay, and remaining are optional. So mnemonic is also called as instruction or opcode. Bracket indicate the fields, optional. And this label. Label means what? If you want to give the starting address of opcode, then you can give the label, and which is followed by colon. Okay. Then this is one of the example where move R5 comma hash indicates the immediate address or the immediate value, means 25 will be loaded into R5. We have already seen such examples. So now we'll see different machine instructions. First one is the data transfer instruction. Means we want to transfer the data from one register to the another register. Then we should use this such a type of instruction. First one is move. We have already seen how to write move instruction to just move data from second register to the first one register, because first is the destination register. Then next one is in out. This is the opcode we are considering. Suppose move is the opcode of the move register, move instruction. Then in and out, input byte or word from port input word to the port. Means if you want to take input or if you want to store the output, then we need to consider in and out instruction. Then LEA, which is stands for load effective address. Okay, so here also load, if you want to load the effective address in the specific register, then we need to use LEA instruction. The next one is LDS and LES. LDS means what? Load pointer using data segment. If the instruction your data is having in the data segment, then you need to use LDS or LES, that is extra segment and the data segment. If you want to use stack, then push and pop instruction we can use. We have already seen this type of instruction we have to use in zero address instruction, where variables are not given or the addresses are not given or specified. Then XCHG means the exchange byte or word. If you want to exchange A is equal to 5 and B is equal to 6, and if you want to exchange the values of A and B, at that time we have to consider such a opcode, that is XCHG. Next is the arithmetic instruction. Means if you want to perform the arithmetic operations, then we need to use such instructions, that is add and sub. Add and sub for addition or and subtraction of any two numbers. Here carry and borrow is not considered. If you want to consider carry and borrow, then you need to write the instruction, that is ADC for addition along with carry and subtraction along with borrow. Then SBB is the instruction format. Then next is INC and DEC. If you want to increment the pointer counter CX, then use INC and DEC for decrement the counter. NEC for negation. If you want to find out 2's complement, then you need to simply use NEG, that is negation of byte. Then next one is for the comparison. If you want to compare two different strings, then use CMP instruction. Multiplication and division, MUL and DIV instruction you need to use for multiply and division. Next, I multiply and I division for integer. Integer multiplication and division, we need to use IMUL and IDIV. Next one is CBW and CWD. Means if you want to convert the data is available in byte to word and word to double word, then we should use the instructions CBW and CWD. Next one is AAA, AAS, AAM and AAD. Then AAA stands for ASCII adjust for addition. Means it converts from BCD to unpacked BCD number. Means when you add two numbers, when you give input through keyboard, that particular number is present in the it is in the form of ASCII, and you need to convert the ASCII into binary or the coded unpacked BCD number. Then that particular syntax should be used for addition, subtraction, multiplication and the division. And last one is DAA and DAC, that is decimal adjust for addition or the subtraction, where we can adjust the decimal value and give the result in the output device. Next one is the logic instruction, where and or an exclusive or an shift or rotate instructions are there. Means first one is not. If you want to find out logical not, then simply use not. And for logical or for logical or for logical exclusive or operation, then SHL and SHR, logical shift rotate instruction, shift left or shift right. If you want to shift one bit left or one bit right, then you should use SHL for left and SHR for right. And if you want to rotate left or right, then you can use ROL and ROR. Next is RCL and RCR, that is rotate left, right through carry byte or word. Then you should use rotate CL and rotate CR. Next is the control transfer. Means what? Looping and jump. Jump statement will be there for the conditional. JMP for jump to the desired instruction. Okay. Then use jump. Then J and 0, that is jump till counter 0, not 0. Till not 0, you have to jump on the statement only. Next one is string manipulation. Means move S, move B, compare S. Move S means what? If you want to move one string into another string, then simply use move S. Move byte, then compare string, scan string, and load store the string into AL. Then LODS. This is the syntax. You can use this type of instruction for move, compare, scan, and load. After that, loop control instruction is there. Means if you want to execute some group of instruction multiple times, then you can use loop. Here LOOP. This is the syntax for loop. LOOPE means if equal. Means if that particular condition is satisfied, till that particular loop will be executed. Okay. After that, loop not equal. Means if you want to execute the instruction, if that particular condition is not satisfied, in that case, you can use loop not equal. That is ENE. And jump if CX not 0. Means you can simply assign CX to 5. Until CX is not equal to 0, you can jump directly on the desired control. Then you can use JCXZ. After that, process control instruction is there. Means flag manipulation, either STC, CLC or CMS. Here, set, clear, complement, carry flag you can use. Means if you want to set carry flag, then you should use STC. If you want to clear the carry flag means what? Carry flag is equal to 1 if after addition carry is generated. Okay. So if you want to set the carry flag as set, clear or complement, then you can use this type of syntax, that is STC, CLC, CMC. After that, STD and CLD to set or clear direction flag. To set or clear direction flag, we can consider this syntax. After that, push F and pop F. If you want to push flag onto the stack or pop flag from the stack, then you can simply use push. Instead of using simple push, you can use push F for push and pop F for pop. This is simple examples written in the assembly program for the addition of any two numbers, where complete program, assembly program is divided into 4 different segments. First one is data segment, second one is code segment, third one is extra segment, and fourth one is stack segment. Okay, but here extra segment and stack segment are not compulsory. Only code segment is compulsory. If you want to give data or if you want to use data in the assembly program, then you can use data segment here. So first 4 lines are the data segment, where I want to add 2 numbers. So I need 2 numbers. So number 1 for first variable, number 2 for second variable. DB stands for the data byte or double byte. Okay, define bytes. So 9H is the value stored in number 1 and 7H is the hex number stored in number 2. Okay, and result, we don't know value of result, so we can consider here question mark, because this program is written to find out the result value. Okay, after that you need to end the data segment with the help of end s. Next is the code segment initialization with the help of this syntax code space segment. And after that, assume DS data and CS code. Here, DS stands for data segment and CS stands for code segment. We need to specify the variable for data and code segment. Here, data is the variable for data segment and code is the variable for assign the variable for code segment. Start is the label. You can give label followed by colon. Okay, so not for all instructions I have used the label. Label is used only one time here because label is not compulsory for writing instruction. This is your first instruction, that is move ax comma data. Here data, where data segment specifies the values of num1 and num2, that data will be moved to accumulator, and after that, that accumulator value, uh, accumulator is right now having num1 and num2, that is 9h and 7h, that will be moved to ds, that is data segment, because we are going to consider the further instructions. For that purpose, your data should be available in the data segment instead of instead of data. Okay, so you have to move it into ds, and after that move al comma num1. So value of num1 will be moved into accumulator, and after that addition instruction is there, add al comma num2, means num1 value is already available in al, and find out the value of find out the addition of num1 and num2, and which is available right now. Addition is available in the al, that is accumulator, and after that move result comma al, means the result al, means addition is stored in al, that will be moved into result right now. And these two instructions, that is move ah comma 4ch and int21, these two instructions are compulsory to write to terminate the operating system, that is OS. And this is an end of end S, means the end the segment, and end start means the end the code segment. Okay, so this is the complete program written in assembly language for addition of any two numbers. Understood? So this is the last slide from my side. Thank you for patiently listening. If any question, you can please ask or you can type in chat box. So thank you, Reena madam. Over to you.
Yes. Anyone having any question? Anyone wants to ask any question? Please ask. Okay. Okay. Thank you, ma'am. It was really very great session. And as you explain each and every concept with the help of the example, so it was really very easy to understand the concept instead of that theory. So on behalf of RSM Polytechnic and IT department, thank you for taking the session and giving your valuable time. It was really very a nice session.
Thank you, madam. Thank you for inviting me. Actually, the
Mm.
topic is very much theoretical. So,
Yes, that's why. No, you have explained it very practically. So it was really very easy to understand each and every concept and directly to the example instead of that theory.
I have added the examples only.
Yeah.
Thank you so much. Thank you so much for listening.
Okay. Okay. Thank you,
And
ma'am.
students, if you have any questions, okay, thank you.
Okay. Okay. Ma'am, can you please share this PPT with us?
Okay, ma'am. I will
Okay.
share.
Okay. Thank you so much, ma'am.
Thank you.
So here I end the session.